Welcome back to the course Rocket Propulsion offered by Adal Systems. In today's class, we will discuss about hybrid propellant rocket engines. So the index for today's class is first we will discuss some basic ideas about hybrid propellant rocket, which will include its advantages, disadvantages, its features, how we can classify hybrid propulsion rockets, etc. Then we will discuss some of the applications of hybrid propellant rockets. Then we will see performance analysis and grain configuration associated with hybrid propellant rockets. And lastly, the combustion instability associated with hybrid propellant rocket engines. So let's begin. So first we will see about hybrid propellant rockets. So the rocket propulsion concept in which one propellant component is stored in the liquid phase while the other is stored in the solid phase are called hybrid propulsion systems. So till now we have seen solid propulsion system and liquid propulsion system. So hybrid is the one where we combine both of them into a single entity, and that's why it is called as a hybrid propulsion system. So hybrid propulsion has been of considerable interest in the commercial rocket business and in space application. This is right because here we are getting advantages of both the solid and liquid propulsion systems. Although hybrids have many unique features of their own, they do benefit from the developments in liquid and solid propellant rockets. Early hybrid motors were produced for target drones and some tactical missiles. Experimental hybrid motors in sizes between 2 and 250,000 lb of thrust have been developed and ground tested. A few of the large and small hybrid motors have flown in experimental vehicles as well. But however, to date, none of larger systems have been selected for production applications. So these hybrid propulsion systems we have seen which were used for some tactical missiles or for some target drones, where we get the sizes of the system from 2 lbf of thrust to 250,000 of thrust. That has also seen in many experimental studies as well. So here to the right we can see a figure of a typical hybrid rocket. So it is a proposed classical configuration design consisting of liquid oxygen hydroxyl terminated polybutadiene, that is HTPB, solid fuel combination intended for space shuttle type of application. So we'll discuss this in the next slide as well. So if we see from top, first we can see that there is one pressurization system, then we have an LOX oxidizer, then systems tunnel, graphite aluminum LOX tank, LOX injector is there, inert HTPB fuel grain, then graphite composite case, combustion ports, mixing chamber, flux bearing TVC, that is thrust vector control, hypergolic igniter. So here as discussed that hybrid is consisting the propellants, one is in liquid form and other one is in solid form. So here the fuel, that is inert HTPB fuel, is used, which is in the solid form, that is fuel grain, and LOX oxidizer, that is liquid oxygen, is used as an oxidizer for this combination. And some distinguishing features of this kind of system is that it is throttleable, we are allowed to use inert fuel grain, and it is having a simple injector geometry. So it has an inert solid fuel grain, a pressurized liquid oxygen feed system, and can be throttled. Multiple ports are required to achieve the large fuel surface necessary for high fuel flow rates. The oxidizer can be either a non-cryogenic, that is storable liquid, or a cryogenic liquid depending on the application and the required specific impulse. In this hybrid propulsion system concept, the oxidizer is injected into a pre-combustion or vaporization chamber upstream of the primary fuel grain. That is, we can see one LOX injector is shown here. So with help of this injector, the oxidizer is injected into a pre-combustion chamber or a vaporization chamber just upstream of the fuel grain region. The fuel grain cavity contains numerous axial combustion ports that generate fuel vapor to react with the injected oxidizer. So the fuel grain which is present, the HTPB fuel grain, it is having many axial ports such that when we inject this LOX oxidizer inside this fuel grain, it is mixed well inside this fuel grain to react and generate the fuel vapor. An after mixing chamber is provided to ensure that all fuel and oxidizer are essentially completely burned before entering the nozzle. So we can see that after the combustion ports, we can see a mixing chamber is provided such that there is no incomplete combustion and fuel and oxidizer are mixed completely at this location, and then they are expanded through a nozzle. So the process or the working principle is very simple, that LOX liquid oxygen is present inside a storable tank which is made of graphite or aluminium. So when we need to start the process, we just have to inject this liquid oxidizer through an injector to the fuel grain such that it moves to all the axial locations or the all axial ports of the fuel grain such that fuel starts to vaporize, and then we use a hypergolic igniter to ignite ignite this combustion such that the fuel and oxidizer is mixed well together inside the combustion chamber, and then it is expanded through the nozzle which is present. So we'll see how this ignition takes place. So a hybrid fuel grain is ignited by providing a source of heat which initiates gasification of the solid fuel grain at the head end of the motor. Subsequent initiation of oxidizer flow provides the required flame spreading to fully ignite the motor. So an hypergolic igniter is used such that we just need to ignite the solid fuel grain at the location where the gasification of the solid fuel grain is initiated, and then it will start to burn itself until all the propellant is consumed. Then ignition is typically accomplished by injection of a hypergolic fluid into the motor combustion chamber. Experimenters describe solid fuels that will ignite spontaneously at ambient temperature and pressure when spread with specific oxidizers other than alloy. Then small hybrid motors such as those used in laboratory environment with gaseous oxygen oxidizer are often electrically ignited by passing current through a resistor such as steel wool located in the combustion port, or by use of a propane or hydrogen ignition system. So one of the example I'll show here, that is an example of a mixture of triethyl aluminum, which is called as TEA, and triethyl borane, which is called as TEB, is injected into the vaporization chamber. The TA-TEB mixture ignites spontaneously on contact with air in the combustion chamber, vaporizing fuel in the dome region. Subsequent injection of liquid oxygen completes ignition of the motor. TA-TEB mixtures are currently used for motor ignition in the Atlas and Delta commercial launch vehicles. So this is the ignition process for a hybrid propellant rocket engine. The concept is very simple, just that the propellants are stored in two different forms and they have to mix thoroughly before they are ignited, and a hypergolic fuel is used to ignite the system. Then we have advantages and disadvantages of hybrid propellant rockets. So advantages that enhance safety from explosion or deterioration during fabrication, storage and operation is achieved. Then start, stop or restart capabilities are there with hybrid propulsion systems. Then relative simplicity, which may translate into low overall system cost compared to liquids, as the systems are very simple compared to liquid propulsion systems. Higher specific impulse than solid rocket motors and higher density specific impulse than liquid bipropellant engines is achieved with hybrid propulsion systems. Lastly, the ability to smoothly change thrust over a wide range on demand is possible with hybrid propulsion systems. Along with advantages, there are some disadvantages for any system. So we'll discuss some of the disadvantages of hybrid propulsion system. This mixture ratio and hence specific impulse may vary during steady state operation as well as during the throttling. Because during throttling we will limit the mass flow rate, and at that time the fuel grain which is half burnt and the oxidizer which is present inside the tank, the mixture ratio will be different, which will affect the specific impulse. The relatively complicated fuel geometries with significant unavoidable fuel residues at end of burn, which somewhat reduces the mass fraction and can vary if there is random throttling. So there will be some fuel residuals leaving behind when we are using throttling, which can affect the mass fraction. Also, the fuel geometries can get complicated. Then prone to large amplitude, low frequency pressure fluctuations, which is termed as chugging. So we'll discuss about this chugging at the end of this presentation. The relatively complicated internal motor ballistics resulting in incomplete descriptions, both of regression rates of the fuel and of motor scaling effects, affecting the design of large hybrid systems. So this is the reason why the hybrid propulsion systems is not used on large vehicles and it is still being used for small scale applications. So next we will see different types of hybrid propulsion systems. So there are presently three distinct configurations of hybrid propulsion systems, that is classical, inverse or mixed hybrid configuration. So the first one, that is classical or typical configuration. By far the most common arrangement is for the fuel to be in the solid phase and for the oxidizer to be stored as a liquid, and many such combinations have been experimentally evaluated. So this is the classical configuration which we know, that is fuel will be stored in a solid form, which we just see, that is HTPP is in solid form and liquid oxidizer is in the liquid form. Second one, that is inverse or reverse configuration. So it has the oxidizer as a solid and the fuel is in the liquid form. While the third one, that is mixed hybrid configuration. So from the word itself we can guess that it will be a mixture of both. So it has a small amount of solid oxidizer embedded into the solid fuel, and the fuel rich mixture is then burned with additional oxidizer injected in afterburner chamber or simultaneously at the head at the end of the grain cavity. So these are the three basic configurations of hybrid propulsion systems which we see today. So the last configuration results from attempts to enhance the regression rates and thus decrease the chamber volume. Increased regression rates can also be obtained in classical configuration with metallized fuel added to the grain. So with the research from classical configuration to inverse configuration and then to mixed configuration has been resulted because of attempts to enhance the regression rates and thus reducing the chamber volume. Also, we can enhance the regression rates in the first configuration itself by using some metallized fuel to the fuel grain. Next, we will see some applications of hybrid propellant rockets. So hybrid propulsion is well suited to applications or missions requiring throttling, command shutdown and restart, long duration missions requiring storable non-toxic propellants, or infrastructure operations, manufacturing and launch that would benefit from a non-self-deflagrating propulsion system. Such applications would include primary boost propulsions for space launch vehicles, upper stages, and satellite maneuvering systems. Many early hybrid rocket motors development were aimed at target missiles and low-cost tactical missiles applications. Other development efforts focused on high-energy upper stage motors. Hybrids have been used to boost a winged manned spaceship. So these are the classical applications of hybrid propellant rockets. Basically a small version of combination of liquid and solid propulsion systems and their applications as well. So in another program, a hybrid motor was developed for high performance upper stage application. Oxygen difluoride was selected as the oxidizer for use with the lithium hydride polybutadiene fueled grain. So this was the combination used for high performance upper stage application. High energy oxidizers include chlorine fluorine compounds such as CIF3 and CIF5. Complementary high energy fuels are typically hydrides of light metals such as beryllium, lithium and aluminium mixed with a suitable polymeric bind. Delivered vacuum specific impulse levels for these high energy hybrid propellants are in the 350 to 380 seconds range depending on nozzle expansion ratio. Combustion efficiencies of 95% of theoretical values have been achieved in tests with this propellant. However, none of these exotic formulation systems have been seen on flight vehicles. A more practical although lower energy upper stage hybrid propellant system is 90 to 95% hydrogen peroxide oxidizer combined with HTPB fuel. Hydrogen peroxide is considered storable for time periods typical of upper stage mission cycles, that is oxidizer tanking to mission completion on the order of several months, and is relatively inexpensive. In solid rocket motors, HTPB is used as the binder to consolidate the aluminium fuel and a 1 perchlorate oxidizer matrix, while in a hybrid, HTPB becomes the entire fuel constituent. HTPB is low cost, processes easily, and will not self-deflagrate under any condition. So this application is for lower energy upper stage hybrid propellant systems where mainly hydrogen peroxide and HTPB fuel is used. Moving on to the next application, a common propellant system for large hybrid booster applications is liquid oxygen, that is LOX oxidizer and HTPB fuel. This hybrid propellant combination produces a non-toxic, relatively smoke-free exhaust and is chemically and performance-wise equivalent to LOX kerosene bipropellant system. This kind of system we have seen in liquid propulsion rocket engines, where this combination gives the best results with less combustion instability and less disadvantages. So same way for hybrid propellants, the LOX and HTPB fuel combination is the best when we compare it with liquid propellant rocket engine. In general, metallized solid fuels are expected to increase performance, but beryllium is very toxic, boron is hard to ignite, lithium has a low heat of combustion, and aluminium oxides increase the molecular mass of the combustion product beyond the temperature range. Hence the search for hydrides and slurries containing these metals to offset the intrinsic disadvantages, but this field is still in the research stages. As far as recently considered liquid oxidizers, hydrogen peroxide, nitrous oxide, and HAN, that is hydroxyl ammonium nitrate, have been considered because of their desirable thermochemical properties and density specific impulse. So till now we have heard that metallized solid fuels gives best performance when they are added with primary propellants, that is solid and liquid propellants, but they have their own set of disadvantages. So that's why when hybrid has come and research is still going on where we can include such kind of metallized fuels and reduce the disadvantages, and in such a way hydrogen peroxide, nitrous oxide and HAN have been considered as liquid oxidizers because of their desirable thermochemical properties and density specific impulse. Whereas smoky exhaust is not determinant, hybrid propellants for certain applications may benefit from the addition of powdered aluminium to the fuel. This increases the combustion temperature, reduces the stoichiometric mixture ratio, and increases fuel density as well as overall density specific impulse. So these were the different applications of hybrid propellant rocket engines featuring different hybrid propellants. Moving on to the next, we will discuss some of the performance analysis and grain configurations. A characteristic operating feature of hybrids is that the fuel regression rate is typically less than one-third that of composite solid rocket propellants. It is very difficult to obtain fuel regression rates comparable to propellant burn rate in solid rocket motors. Consequently, practical high-thrust hybrid motor designs must have multiple perforations, that is combustion ports, in the fuel grain to provide the required fuel surface area. The performance of a hybrid motor, which is defined in terms of delivered specific impulse, depend critically on the degree of flow mixing attained in the combustion. Multiple combustion ports serve to promote high combustion efficiency as a result of the turbulent mixing environment for unreacted fuel and oxidizer in the mixing chamber region downstream of the fuel grain. Much of the technology from liquid and solid propellant rockets is directly applicable to hybrid rockets, but the main difference lies in the driving mechanisms for solid propellant burning and hybrid fuel regression. In a solid system, the oxidizer and fuel ingredients are well mixed during the propellant manufacturing process, and combustion occurs as a result of heterogeneous chemical reaction on or very near the surface of the solid propellant. So the fuel regression rates in hybrid propellants are less than one-third that of composite solid rocket propellants, and it is very difficult to obtain fuel regression rates comparable to propellant burn rates in solid rocket motors, because the performance of hybrids depends on the degree of flow mixing attained in the combustion chamber. Because we are using a solid fuel and a liquid oxidizer, so there might be a problem with the mixing and which may not be uniform. So that will affect the specific impulse which is delivered by the hybrid propulsion system. So to attain this high combustion efficiency in hybrid propellant rocket engines, multiple combustion ports has to be done, because that will promote turbulent mixing for unreacted fuel and oxidizer in the mixing chamber region downstream of the fuel grain. Then in hybrids with metallized fuel grains, radiation from the metal oxide particle cloud in the combustion port contributes a major portion of the total heat flux to the fuel grain. The local regression rate of the fuel is also quite sensitive to the general turbulence level of the combustion port gas flow. Localized combustion gas eddies or recirculation zones adjacent to the fuel surface act to significantly enhance the regression rate in these areas. So that's why recirculation zones are created near the fuel surface region, which is close by to the injector, such that the regression rates are increased in such areas. Hybrid fuel regression rate is thought to be insensitive to fuel grain bulk temperatures over the range in which solid rocket motors may operate, that is from -65 to 165 degree Fahrenheit. This is due to the absence of heterogeneous fuel oxidizer reactions at the fuel surface, in which the reaction rates are temperature dependent. So this happens in solid propellants, and because over the above temperature range the change in heat content of the solid fuel is small compared to the heat necessary to initiate vaporization of the fuel surface. So the number of combustion ports required in a motor optimization problem that must account for the desired thrust level, acceptable shifts in mixture ratio during burn, motor length and diameter constraints, and desired oxidizer mass velocity. So how much combustion ports a hybrid propulsion system should include is an optimization problem which includes many different parameters like desired thrust level and acceptable shifts in mixture ratio during burn, motor length and diameter constraints, and desired oxidizer mass velocity. So the hybrid rocket motor design typically begins by specifying a desired thrust level and a propellant system. That is, first we have to specify what desired thrust we need and what propellant system we are going to use. Subsequently, selection of the desired operating oxidizer to fuel mixture ratio determines the propellant characteristic velocity. So based on what propellant we are using, then we can specify our operating oxidizer to fuel ratio, which will give us the characteristic velocity of the propellant. Once the characteristic velocity and mixture ratio are specified, the total propellant flow rate and the subsequent split between oxidizer and fuel flow rates necessary to produce the required thrust level can be computed. The necessary fuel flow rate in hybrids is determined by the total fuel surface area, that is perimeter and length of the combustion port, and the fuel regression rate. So this is how the propulsion system is designed for hybrid rocket motors. So the fuel regression rate is primarily determined by the oxidizer mass velocity, which is also called as oxidizer flux. Thus the fuel flow rate is intrinsically linked to the oxidizer flow rate and cannot be independently specified as in a liquid rocket engine. So to find out the necessary fuel flow rate in a hybrid rocket, we need the total fuel surface area and the fuel regression rate. Then the fuel regression rate is determined from the oxidizer flux. So that's why the fuel flow rate is directly linked to oxidizer flow rate and cannot be independently specified as we do in liquid rocket engines. Selection of fuel ingredients can also have a significant impact on grain regression rate, which is largely a function of the energy required to convert the fuel from solid to vapor phase. And this energy is called the heat of gasification, and for polymeric fuels includes the energy required to break polymer chains, it is heat of depolymerization, and the heat required to convert polymer fragment to gaseous phase, that is heat of vaporization. The term heat of vaporization is often used as a catch-all phrase to include all decomposition mechanisms in hybrid fuels. So this was all about performance analysis. Next we will discuss about combustion instability in hybrid propellant rocket motors. So the hybrid combustion process tends to produce rough pressure versus time characteristics. However, a well-designed hybrid can typically limit combustion roughness to approximately 2 to 3% of mean chamber pressure. In any combustion device, pressure fluctuations will tend to organize themselves around the natural acoustic frequencies of the combustion chamber or oxidizer feed system. While significant combustion pressure oscillations at chamber natural mode acoustic frequencies have been observed in numerous hybrid motor tests, such oscillations have not proved to be an insurmountable design problem. When pressure oscillations have occurred in hybrid motors, they have been observed to grow to a limiting amplitude which is dependent on such factors as oxidizer feed system and injector characteristics, fuel grain geometric characteristics, mean chamber pressure level, and oxidizer mass velocity. Unbounded growth of pressure oscillations such as may occur in solid and liquid rocket motors has not been observed in hybrid motors yet. So the combustion instabilities which we discussed in solid rocket motors and liquid rocket motors, such kind of instabilities are not occurred or not seen yet in hybrid motors, but significant combustion pressure oscillations at chamber natural mode acoustic frequencies has been observed in hybrid motor tests, but they have observed to grow to a limiting amplitude which is dependent on many factors like oxidizer feed system and injector characteristics, what fuel grain we are using and what are its geometric characteristics, then mean chamber pressure which we are achieving, and oxidizer mass velocity at which it is flowing. So hybrid motors has exhibited two basic types of instabilities in static test environments, that is oxidizer feed system induced instability, which is considered as non-acoustic, and second one, that is flame holding instability, which is considered as acoustic instability. So the oxidizer feed system instability is essentially a chugging type and arises when the feed system is sufficiently soft. So the first instability that is arised or induced because of oxidizer feed system is when the feed system is sufficiently soft. That is, here in figure we can see two figures are given. That is, first one is periodic large amplitude low frequency combustion pressure oscillations are an example of oxidizer feed system induced chuck type combustion instability in a 24-inch diameter alloy HTPB motor. So on x-axis we have time from motor start, that is in seconds, and on y-axis we have pressure. So we can see in between 1 to 15 seconds of duration, this chugging type of instability which is arise because of oxidizer feed systems is visible in the first graph, that is A. There are pressure oscillations simultaneously occurring in this amplitude, while the second one is an example of stable combustion in a 24-inch diameter LOX HTPV motor exhibiting an overall combustion roughness level of 1.3%. While as in the second figure we can see that along the x-axis, as the time is increasing, even the pressure oscillations are getting reduced and the combustion is occurring at a stable roughness. So what we can do to avoid such kind of instabilities, that is stiffening the feed or injection system, can eliminate this oscillation. This is accomplished by increasing the injector pressure drop, thus making propagation of motor pressure disturbances upstream through the feed system more difficult and eliminating sources of compressibility in the feed system. Chugging type instabilities in hybrid motors have proven amenable to analysis in terms of prediction and prevention. Moving on to the next instability, that is flame holding instability, which is relevant to hybrid motors, was first observed during the development of solid fuel ramjets. Flame holding instabilities in hybrids are typically manifested at acoustic frequencies and appear in longitudinal modes. So in figure here we can see that on x-axis we have frequency and y-axis we have pressure, which shows a frequency versus amplitude plot at successive time intervals for an 11-inch diameter GOX HTPV motor test. Shows pressure oscillations in the motor first longitudinal acoustic mode at 150 Hz due to flame holding instability. So at 150 Hz of frequency we see a flame holding instability is occurring, that is there are some pressure oscillations but they are dying out soon and mostly they are occurring at the longitudinal mode. No acoustic instabilities in hybrid motors have been observed in higher frequencies, tangential or radial modes such as we have seen in solid rocket motors or liquid engines. Flame holding instabilities arise due to inadequate flame stabilization in the boundary layer and are not associated with feed system flow perturbation. It is apparent that flame holding instability can be eliminated by several means, all of which act to stabilize combustion in the boundary layer. So because there is no better flame stabilization in the hybrid propulsion combustion, this instability arises, but still there are various ways where we can eliminate this kind of combustion instability. Because of improper flame handling capability of the engine, we must have to stabilize the flow in the boundary layer to avoid this kind of instability. So how we can achieve that, we will see. That is, the first method is to use a pilot flame derived from injection of a combustible fluid such as hydrogen or propane to provide sufficient oxidizer preheating in the leading edge region of the boundary layer flame zone. With this technique, motor stability characteristics are relatively insensitive to the nature of the injector flow field. The second method involves changing the injector flow field to ensure that a sufficiently large hot gas recirculation zone is present at the head end of the fuel grain. Such a zone can be created by forcing the upstream flow over a rearward facing step or by strong axial injection of oxidizer. So here we can see two diagrams are given based on how we are attempting the flow inside the combustion chamber. So first one shows axial injection of oxidizer results in a strong hot gas flow recirculation zone at the fuel grain leading edge, producing stable combustion. So the axial injection of oxidizers is giving the stable combustion in the first figure, while conical injection of oxidizer can produce a weak or non-existing hot gas flow recirculation zone at the fuel grain leading edge, resulting in an unstable combustion. So instead of giving a coaxial flow for hybrid rocket motors, we can use a simple axial injector to inject the oxidizer into the fuel grain. So this way we can avoid the flame instability which is occurring in hybrid rocket motors. Despite recent advances in understanding causes of and solutions for combustion instability in hybrid motors, development of a comprehensive predictive theory of combustion stability remains one of the major challenges in hybrid technology development. So despite being in such an advanced decade, still developments has to be made for a predictive theory of combustion instability for hybrid technology motors. So the summary for today's class is that first we have discussed about an overall idea about hybrid propellant rocket engines, that is the working principle, the several components which are used, how is the ignition process, the advantages and disadvantages of using such propulsion systems. Then we have discussed about three configurations of hybrid propulsion systems. that is classical, inverse, and mixed hybrid configurations. Whereas in classical, we have seen that fuel is present in solid form and oxidizer in liquid form, while for the inverse, they both are shuffled, that is, fuel is present in liquid form and oxidizer is present in solid form. And for the third one, both are mixed together. Then we have seen different applications of hybrid propellant rocket engines with variety of propellants. That is, for high performance upper stage applications, we have seen different propellant combination is used. Whereas for lower energy applications, some different combination is used. Then we have seen booster applications as well. Then we saw different performance analysis parameters and the required grain configuration for a hybrid system. Also, we discussed about combustion instabilities occurring in hybrid systems with their features, their occurrence magnitudes, and remedies to prevent them, where we saw oxidizer feed system induced instability and flame holding instability. So this covers the hybrid propellant rocket engines, and the references for today's class are present here. In next class, we will start with electric propulsion. Thank you.